In this video, we will discuss ways to use storage to reduce time of use charges from the utility companies. Time of use load shifting is being discussed quite a bit these days in order to reduce our electricity costs. Time of use load shifting is a concept where you shift the use of electricity from the utility companies when costs are higher to when they are lowest. Let's investigate if the potential savings are worth the effort. Let's review typical energy consumption. Here is an example showing how we consume electricity during the day with the peak consumption in the morning and evening hours. Let's compare this to what our utility company charges. Here's an example of time of use rates during the summer in Ottawa, Canada. In winter, the on-peak charges will occur at different times in the day compared to the summer charges. If we want to maximize the use of storage to offset our utility charges, we need to charge our batteries during the lower cost off-peak times from 7 p.m. to 7 a.m. Then use the stored energy when the utility rates are highest from 7 a.m. to 7 p.m. Here is an actual bill with the energy consumption in blue according to off-peak, mid-peak, and on-peak. The billing charges for the same blocks are in red. These were reviewed in greater detail in Part 7 of this series. The three blue bars represent the original consumption. If we take just the on-peak consumption and shift it to the off-peak, we see the remaining red bars. In this example, we can save $10.41. If we also shift the mid-peak charges to off-peak, we see the remaining orange bar on the right, a further $6.05. If we could achieve the same amount of savings each month, then over the year we would save almost $200. Sounds great so far, but how can we achieve this? If we look at daily consumption, we need a storage of 4.3 kilowatt hours to shift the on-peak consumption, and a further 5.6 kilowatt hour storage for the mid-peak consumption, totaling approximately 10 kilowatt hours. Let's dig into the details. We don't have a breakdown of use according to time of day, so we can only look at averages. We only need to look at the output requirements for mid and on-peak. This could be achieved with a 1 kilowatt inverter. Therefore, we can use a 1 kilowatt inverter with 5 kilowatt storage for on-peak time shifting and 10 kilowatts if we include mid-peak shifting. So for 10 kilowatt hours, how many 12-volt batteries is that? 10 kilowatt hours divided by 12 volts is 833 amp hours. 100 amp hour batteries can be discharged to 50%, meaning 50 amp hours usable per battery. Take 833 amp hours divided by 50 amp hours per battery equals 16.7, or 17 100 amp hour batteries. Another issue to consider is recharge time. It will take about 12 hours to recharge the batteries, provided that you have a strong charger. So we have just about the right time, unless in your area the off-peak times are shorter. Great, our puzzle is taking shape. Except, how would such a system work? What kind of equipment would you need? First, the inverter needs to be grid tied. Remember that it's only a 1 kilowatt inverter. So if someone tries to do laundry, use a hairdryer, toaster, microwave oven, washer, dryer, etc., you're toast. If you want to stay off-grid, the solution is a 5 kilowatt inverter. Except that using high energy would drain your batteries faster, which means that they wouldn't last the entire peak period, and you would need to go grid tied again, which would charge your batteries during peak periods. Well, you could get more storage. Now the cost of the inverter and storage are mounting, and the concept of saving money from time of use load shifting goes out the window. So we need to have a grid-tied inverter. We need to know when to charge batteries and when to power the home. That's straightforward because it's based on time of day. To use the storage to power the house in peak times, the inverter must be programmed to be in output mode and not in charge mode. The way to have current flow from the inverter is to set a higher voltage than the grid voltage. The inverter requirement just grew to include a programmable output versus charge mode and a programmable output voltage. How does the inverter know how much power to output if the grid is on? To achieve maximum savings, the output needs to match the consumption. But how do we know what the consumption is? If we could program the inverter to limit the output to a 1 kilowatt maximum, that could work. But what happens when the home consumption is below 1 kilowatt? Does the extra current now flow to the grid? There's another issue. This is a little complicated, so I will try to keep this simple. We are powering loads in our home using a distribution system called an electrical panel. The electricity from the grid comes into the home and splits into two 120 volt AC phases, left and right, plus a null. Rooms in our home are either connected to the left or right side of the panel. You would think that if we consume 1 kilowatt of energy, and if our special inverter pumps an equal 1 kilowatt of energy into the panel, then the energy supplied from the grid would be zero. Except in the case where the left and right sides consume a different amount. If the right loads consume 800 watts and the left consumes 200, some of the current will flow in the null wire to the transformer and back down to the right side of the panel. Except that the transformer is located on the pole outside your home, on the other side of the meter. So you won't get credit for the electricity flowing in the opposite direction through the meter, but you will be charged when your own energy flows back into the panel. It's nobody's fault, that's just the way electricity flows. You can't stop the flow of AC current in the opposite direction because by definition, AC current flows back and forth. So to further complicate issues, we need to balance our loads. Electricians do load balancing when they wire an electrical panel, but you can't expect them to factor the loads used during on-peak times. Oh, I almost forgot. One last issue. Remember this table? We are trying to save $200 a year based on the $16.44 savings a month. Charging and discharging batteries has a typical turnaround efficiency of about 80%. It takes more energy to charge a battery than what you can store in the battery. Then there is another loss converting this DC energy in the battery to usable AC. So for a 1 kilowatt hour that you consume to charge a battery, you only get to use 800 watt hours. In order to get the number you want, you need to add 25%. When you factor in an additional 25%, the benefits are reduced to $130 a year. As you can see, there are many things to consider in making time of use load shifting practical. If the difference between on and off peak charges increases, and as batteries and inverters improve in cost and efficiency, someday it will be practical. Lots of companies are working on these and many more technical issues. Stay tuned. Thanks for watching.